Already we had discussed module 1 of chapter 4. The title of the chapter 4 was characterization of Banach spaces. In module 1 we have discussed on convex sets. Today we shall discuss on module 2 of chapter 4. The title of module 2 of this chapter is equivalent norms and series in Banach spaces. Given a linear space, we shall define a norm, and simultaneously we shall also define a norm which is equivalent to the norm already defined on a linear space, and we shall show some basic results on equivalent norms. Also in this module we shall discuss on characterization of completeness of a nonlinear space in terms of the infinite series. That is why a nonlinear space is complete whenever an infinite series is convergent. In this module 2, we shall discuss on equivalent norms and series in Banach spaces. First of all, we shall define an equivalent norms. Let capital X be a linear space. A norm, that is norm 1 on X, is said to be equivalent to a norm 2 on X if there are positive reals A and B such that for all X belonging to capital X, we have A into norm of x2 is all less or equals to norm of x1 is less or equals to b into norm of x1. This is equation number 1. Note that the role of norm 1 and norm 2 can also be interchanged in equation 1. Now, we shall give a theorem. Let capital X be a finite dimensional nonlinear space, then any two norms, norm 1 and norm 2 on X are equivalent. The proof goes below. Let dimension of X is equal to n, say. So, there are n numbers of basis vectors, and we have assumed that E1, E2 dot En be a basis for capital X. If X belonging to capital X, then X can be represented uniquely in the form X is equal to alpha 1 E1 plus alpha 2 E2 plus plus alpha n En for some scalars alpha 1, alpha 2, comma comma alpha n. So, there is a constant C greater than 0 such that norm of x1 greater or equals to C times modulus of alpha 1 plus modulus of alpha 2 plus plus modulus of alpha n. Already this result comes due to a lemma already been discussed. If capital R is equal to max of norm of Ej under the norm 2 and maximum is taken over 1 less or equals to j less or equals to n, then norm of x2 is equal to norm of sigma j equal to 1 to n alpha j Ej under the norm 2, which is less or equals to sigma j equal to 1 to n norm of alpha j Ej under the norm 2 is equal to sigma j equal to 1 to n modulus of alpha j norm of Ej under the norm 2, which is again less or equals to r into sigma j equal to 1 to n modulus of alpha j is equal to r by c norm of x under norm 1, implying that c by r into norm of x under norm 2 is less or equals to norm of x under norm 1. The other half of the desert inequality 1 comes by interchanging the norms norm 1 and norm 2. Thus, we see that norm 1 and norm 2 are equivalent on capital X. Let us take an example. Consider a norm-linear space R2, that is Euclidean 2 space of reals with two norms, that is norm 1 and norm 2 defined by norm x comma y pairwise taken under the norm 1 is equal to root over x square plus y square, and norm of pair x comma y under the norm 2 is equal to max of modulus of mod x comma modulus of y for pair of elements x comma y belonging to R2. The solution is given below. We have for pair x comma y belonging to R2, modulus of x square is less or equals to modulus of x square plus modulus of y square, and modulus of y square is less or equals to modulus of x square plus modulus of y square. Thus, norm of x comma y under the norm 2 is equal to max of modulus of mod x comma modulus of y is less or equals to root over modulus of x square plus modulus of y square, which is again equals to root over x square plus y square, and that is equal to norm of x comma y under the norm 1. That means norm of x comma y under the norm 2 is less or equals to norm of x comma y under the norm 1. This is equation number 2. Again, norm of x comma y whole square under the norm 1 is equal to x square plus y square is equal to modulus of x square plus modulus of y square, which is again less or equals to 2 times max of modulus of x comma modulus of y whole square is equal to 2 into norm of x comma y under the norm 2. That means norm of x comma y under the norm 1 is less or equals to root over 2 of norm of x comma y under the norm 2. This is equation number 3. Combining the equation 2 and 3, we have norm of x comma y under the norm 2 is less or equals to norm of x comma y under the norm 1 is less or equals to root over 2 norm of x comma y under the norm 2. We have learnt that any two norms on a finite dimensional nonlinear space are equivalent. We know that the finite dimensional space Cn, that is Euclidean n space over the field of complex numbers, is a finite dimensional space. Now, if we take norms, that is norm 1 is equal to sigma mod of xi I, where x is equal to xi1, xi2, xin, that is n tuples, and if we take norm 2, that is norm of x2 is equal to sigma I equal to 1 to n modulus of xi I square to the power half, and if we take another norm, that is norm of x3 is equal to maximum of modulus of xi I equal to 1 to up to n, we see that any two norms, that is norm 1 norm 2 or norm 1 norm 3 or norm 2 norm 3 are equivalent. Also, we have given a definition on topological invariant property. If we take two norms, that is norm 1 and norm 2 in a nonlinear space X, then every Cauchy sequence with respect to nonlinear space, that is under the norm 1, is equivalent to the Cauchy sequence in norm 2 of a nonlinear space X. Similarly, the convergence sequence xn in a nonlinear space X under the norm 1 is equivalent to the convergence of a sequence in a nonlinear space X under the norm 2. Let norm 1 and norm 2 be two equivalent norms on a linear space capital X. Then X under norm 1 is a Banach space if and only if X under norm 2 is so. That is, X under norm 2 is also a Banach space. This is true vice versa. B, a set is bounded in X under norm 1 if and only if it is bounded in X under norm 2. The proof goes below. Let X under norm 1 is a Banach space. Let Xn be a Cauchy sequence in X under norm 2. Then for each epsilon greater than 0, there exists a positive integer capital N such that norm of Xn minus Xm under the norm 2 is strictly less than epsilon for all n comma m is greater or equals to capital N. Since norm 1 and norm 2 are equivalent norms on capital X, there exists a constant k1 greater than 0 such that k1 into norm of xn minus xm less or equals to norm of xn minus xm under the norm 2 is less than epsilon for all n comma m greater or equals to capital N, implying that xn is a Cauchy sequence in X under norm 1. But X under norm 1, that is nonlinear space X under norm 1 being complete, sequence xn converges in X under norm 1. Let norm of xn minus x tends to 0 as n tends to infinity, the norm is taken under the norm 1. Again, by equivalence of two norms, norm 1 and norm 2, we find a constant k2 greater than 0 such that norm of xn minus x under the norm 2 is less or equals to k2 into norm of xn minus x, which goes to 0 as n tends to infinity. Hence, x is a Banach space under the norm 2. The converse part follows similarly by interchanging the role of norm 1 and norm 2. Now, for the proof of B, let B is a subset of X and it is bounded in X under the norm 1. Then there exists a constant capital M greater than 0 such that norm of X under the norm 1 is less or equals to M for all X belongs to capital B. As norm 1 and norm 2 are equivalent norms, there exists a constant alpha greater than 0 such that norm of x under norm 2 is less or equals to alpha times norm of x under norm 1, which is again less or equals to alpha into capital M for all x belongs to capital B. Hence, B is bounded in a nonlinear space X under the norm 2. In this connection, let us take a note. This completeness and boundedness of sets are linear topological invariant properties of nonlinear spaces. Now, we shall introduce an infinite series on a nonlinear space, and with this introduction of the infinite series, we shall give the characterization of a completeness of a nonlinear space, and thereby we shall show that when a nonlinear space will be a Banach space under the convergence of an infinite series. Let us take X be a nonlinear space, and let us take a sequence of elements xn, and we take an infinite series sigma n equal to 1 to infinity xn, where xn belonging to capital X. Now, we shall take a partial sum denoted by Sn, which is equal to x1 plus x2 plus dot 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 plus xn. Now, we say that the infinite series sigma n equal to 1 to infinity xn, where xn belonging to capital X converges to an element S belonging to capital X if and only if the sequence Sn, where Sn is equal to x1 plus x2 plus dot dot plus xn converges to S. That means, norm of Sn minus S tends to 0 as n tends to infinity. That means, for every epsilon greater than 0, there exists a positive integer capital N such that norm of Sn minus S is strictly less than epsilon whenever n is greater or equals to n, that is n greater or equals to capital N, where n is a positive integer. And we write in this case sigma n equal to 1 to infinity xn is equal to S, and S will be called the sum of the infinite series sigma n equal to 1 to infinity xn. That means, limit n tends to infinity Sn is equal to S, where Sn is equal to x1 plus x2 plus dot 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 plus xn, and S is equal to sigma n equal to 1 to infinity xn. Now, Sn is called the nth partial sum of the infinite series sigma n equal to 1 to infinity xn. Now, let us take a theorem. Let series, that is sigma n equal to 1 to infinity xn, be an infinite series in a Banach space capital X. Then the series sigma n equal to 1 to infinity xn converges if and only if for each epsilon greater than 0, there exists a positive integer capital N such that norm of xn plus 1 plus xn plus 2 plus dot 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 plus xn plus k is strictly less than epsilon for all n greater or equals to capital N and k equal to 1, 2 and so on. The proof goes below. Let us take a partial sum Sn is equal to x1 plus x2 plus dot 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 plus xn. Then Sn plus k minus Sn is equal to xn plus 1 plus xn plus 2 dot 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 plus xn plus k. So, the condition of hypothesis asserts that Sn is a Cauchy sequence in X, and by completeness of capital X, we see that sequence Sn converges to an element of capital X, that is sigma n equal to 1 to infinity xn is convergent. The converse part follows trivially. Now, let us take a definition. An infinite series sigma n equal to 1 to infinity xn in a nonlinear space capital X is said to be absolutely convergent if and only if the infinite series sigma n equal to 1 to infinity norm of xn is convergent. In this connection, we get a theorem. A nonlinear space capital X is a Banach space if and only if every absolutely convergent series in capital X is convergent. By an absolutely convergent series, we mean that an infinite series sigma n equal to 1 to infinity xn in X if and only if the infinite series sigma n equal to 1 to infinity norm of xn is convergent. The proof goes below. Let capital X be a Banach space and let sigma n equal to 1 to infinity xn be an absolutely convergent series in X. As sigma n equal to 1 to infinity xn is absolutely convergent, by definition sigma n equal to 1 to infinity norm of xn is convergent. That means, for every epsilon greater than 0, there exists a positive integer capital N such that norm of xn plus 1 plus norm of xn plus 2 plus dot dot norm of xn plus k is strictly less than epsilon for all n greater or equals to capital N, k equal to 1, 2 and so on. Now, by triangle inequality in a nonlinear space, norm of xn plus 1 plus xn plus 2 plus dot 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 plus xn plus k is less or equals to norm of xn plus 1 plus norm of xn plus 2 plus dot 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 plus norm of xn plus k, which is again less than epsilon by the above condition, and it is true for all n greater or equals to capital N. So, the series, that is sigma n equal to 1 to infinity xn is convergent. Conversely, let capital X be a nonlinear space in which every absolutely convergent series in X is convergent. We shall now show that X is a Banach space. Let sequence xi be a Cauchy sequence in X. Then we can find a sequence of positive integers nk with n1 less than n2 less than nk less than and so on, such that norm of xn plus k minus xnk is strictly less than 1 by 2 to the power k, where k is equal to 1, 2 and so on. It is possible due to, that means for every positive integer k, we can find n1 less than n2 less than nk less than so on, such that norm of xn plus k minus xnk strictly less than 1 by 2 to the power k, where k runs from 1, 2 and so on, and therefore, sigma n equal to 1 to infinity norm of xn k plus 1 minus xnk is convergent. Already we have norm of xn k plus 1 minus xnk is less than 1 by 2 to the power k. If we take sigma both sides, that is k equal to 1 to infinity, we see that series k equal to 1 to infinity 1 by 2 to the power k is convergent. So, by comparison test, sigma k equal to 1 to infinity norm of xn k plus 1 minus xnk is convergent. Since every absolutely convergent series is convergent, we see that sigma n equal to 1 to infinity norm xnk plus 1 minus xnk is convergent, which implies that sigma n equal to 1 to infinity xnk plus 1 minus xnk is absolutely convergent in capital X. and hence by assumption sigma k equal to 1 to infinity x n k plus 1 minus x n k is convergent in capital X. Thus, nth partial sum, that is Sn is equal to xn2 minus xn1 plus xn3 minus xn2 plus dot 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 plus xnk plus 1 minus xnk, which is equal to xnk plus 1 minus xnk. This is possible by mutual cancellation, and this Sn is convergent, and hence sequence xnk is convergent. Thus, the Cauchy sequence Xn has a convergent subsequence Xnk, k equal to 1, 2 and so on, and is therefore convergent. Hence, capital X is complete and consequently X is a Banach space. In this connection, let us take a problem. If sigma n equal to 1 to infinity Xn be absolutely convergent series in a Banach space capital X, then norm sigma n equal to 1 to infinity Xn is less or equals to sigma n equal to 1 to infinity norm of Xn. Now, let us take a solution. Let k equal to 1 to infinity xk be an absolutely convergent series in capital X. Then sigma k equal to 1 to infinity xk is convergent in X, because every absolutely convergent series in X is convergent. Now, we have norm sigma k equal to 1 to n xk is less or equals to sigma k equal to 1 to n norm of xk. This is possible due to the triangle inequality in a nonlinear space. And letting n tends to infinity, and since norm function is continuous, we get norm sigma k equal to 1 to infinity xk is less or equals to sigma k equal to 1 to infinity norm of xk. Now, in this module what we have learnt? We have learnt equivalent norms, and we have learnt some definitions of equivalent norms and some basic results on it, and also we have cited some examples of equivalent norms. Also, we have proved on a result some topological invariant property on a equivalent norms. Also, we have introduced an infinite series on a nonlinear space, and we have shown that infinite series is convergent under what condition. We have learnt an absolutely convergent series. We have given a definition that absolutely convergent series, convergence of a series. We have proved a result on the series on a nonlinear space, that every absolutely convergent series is convergent. Also, we have proved on a result, that is the completeness criteria of a nonlinear space. Under what condition a nonlinear space will be complete, that is a nonlinear space will be a Banach space. So, in this connection we have proved a result that a nonlinear space is a Banach space if and only if every absolutely convergent series is convergent. With this, we now come to an end of this module 2.